Hi everyone, this is Raymond, one of the teaching assistants of the course 4460 Relativity, and I will be responsible for our first exercise class, and I believe that the purpose of the exercise class is to help you go through our problem sets. So I'm going to go through the problem set 1 with you. I believe that you're already able to look at the problem set 1 because it should have been uploaded to the Blackboard. Let's go through it very quickly. So as you can very quickly see that there are 3 parts to the problem sets. Okay, short questions, intermediate questions, and long questions. Okay, and I won't go through the first part with you because most of them are pretty straightforward. If you have attended the lecture by Professor Lee, you should be able to clear all these questions. And for the second part, intermediate questions, I can give you some hint to some of it. So maybe take some time to look at it together. So basically, there are 2 questions here. The first question is about a curve. Okay, it is described by RU. And at any given point on the curve, the tangent vector is given by dr by du. So the first question is to ask us to show that if the parameter u is the arc length s, then the tangent vector defined this way would be a unit vector. I won't give any hints here because this is also quite straightforward from some material from the lecture. So please feel free to go back to the lecture notes and find the definition here. The definition of the arc length. From the definition of arc length, you should be able to derive this. And the second part of the question is asking us to show that this tangent vector t is actually perpendicular to the principal normal, which is defined this way. My quick hints here would be, first, let's recall what would be the test to test whether 2 vectors are perpendicular to each other. Okay, number 1. And the second hint would be lying here, because as you can see from the definition of the principal normal here, derivative of the vector, the tangent vector with respect to s is involved. So you may want to differentiate something with respect to s to get the result. Okay. So that's all I can say. So take some time to think about it. Okay. And I believe that you can derive the result. And the second question in the second part is actually also quite straightforward. I won't go into the details, but basically it's asking to derive the scalar product between 2 vectors, okay, namely E1 here, which is defined as this way, and epsilon I. I pronounced it wrongly. It is EI here, okay, defined this way, and epsilon I here, defined this way. It's actually the gradient, okay. So basically, if you can write explicitly both of these vectors, and then you take the scalar product, then you should be able to derive the result. Okay, so it's also pretty straightforward. Okay, coming to the third part, actually it's also quite straightforward. Okay, let's look at it together. So basically, it's about a surface, a hyperboloid, and the hyperboloid is defined this way, and the parameter is given by this expression here. Okay, so if you don't have any picture about this, actually, okay, let's recall what a surface is, right? So a surface if you want to visualize the surface, we can visualize the surface in a three-dimensional space. Okay, and basically a surface in such a three-dimensional space is nothing but just a collection of some points, right? It's a collection of points which lie in the surface, okay? And the point in the three-dimensional space can always be given by three numbers, right? X, Y, Z here, okay? So this is the Cartesian expression. This would be the most straightforward and most understandable way to give the coordinates, okay? So they are given here, and the X, Y, Z here is actually parameterized by this expression here, okay? So basically what this means here is we have two parameters, okay, theta and phi. Okay, so because we are talking about a surface, so actually we can, or we should have at least two parameters to represent the points on the surface. And in this case, the two parameters would be theta and phi. So this is the way that we parameterize this surface. And of course, ABC here are constants, okay? And the first question is straightforward. Basically, it just asks you to derive the area element on this surface, right? To show that this area element is given by this expression. So now I won't go into details about how to derive this. Instead, I will show you the exercise notes I have prepared here. Okay, by the way, I don't know if you prefer me do handwriting to explain things, but I apologize, I don't have a writing device, so I just prepared this note. I hope that this would be helpful. Okay, so this note is basically contains what I just said for part A and part B. And then for part C, coming back to part C, let's look at this formula. Okay, so this formula should be something that you have already discussed in the lecture. Okay, so that's why I said the question is quite straightforward. Basically, you just apply this area elements formula to see whether it's really expressed this way, right? To give you the workflow, I would give you an outline by using an example, which is not the hyperboloid, but just a sphere of radius A. Okay, so let's derive the area element of a sphere of radius A. And actually, we should know the answer already, right? From the vector calculus course before, right? Because if you can recall, the answer is actually these things here. Okay, if the radius of the sphere is A, then the area elements is given by these things, right? Because you know, we can multiply the size, okay, the two sides of the elements to get these things. And one side would be the line element along the theta direction. And the theta here means the polar angle, okay, running from the North Pole, okay, and then 90 degree to the 90 degree to the horizontal plane, and then another 90 degree to the South Pole, right? So this line element is along this direction, and the other element, which is along the phi direction or the azimuthal direction, would be these things, and their product would give this answer, right? But anyway, let's try to use this formula to derive the result or to verify whether it is this thing here. So basically, it's very straightforward. We just try to find the XYZ, okay, the point on the sphere in terms of theta and phi, okay, the two parameters that we use to parameterize the sphere. And again, from the vector calculus course, you should be able to recall that x, y, z are expressed in terms of these three things here, respectively. Okay, if you forget why this is so, maybe you can refer back to vector calculus. Okay, but anyway, for this question, you don't need to derive this because it's already given. Okay, here. Okay, it's already given here. But for the sphere here, I just trying to demonstrate the workflow to you. Okay, so now we have x, y, z in terms of theta and phi. And now actually we can directly derive this formula for the sphere. Because if you can recall from the lecture, u and v here is nothing but just the parameters that we use to parameterize the surface. And in this case, it's nothing but theta and phi, right? So we can just first find out round r by round theta, which is here. And then another thing is round r by round phi, right? We replace theta to u and phi to v, okay? And then it should be very straightforward, right? We just differentiate this whole vector r here with respect to theta and with respect to phi, okay? So you should be able to derive them, and these are the results. So, so note that these two things are vectors, right? Because r here is vectors. You differentiate each of the component, you get a vector, right? So now we have these two vectors, and then we can just plug in these two vectors into the formula of the area elements here, which will read something like this, okay? So this would be a cross product, right? And the second line here is nothing but just the formula for the cross product, okay? If you can recall, the two vertical lines, the inner vertical lines here is just the determinant of the matrix-like thing here, okay? And this is just a convenient way to compute the cross product, okay? And the outer vertical lines here are nothing but just the magnitude operator here, right? From the formula, okay? So we first compute the cross products, okay? Which should be straightforward if you're familiar with the procedure of getting the cross product between two vectors. And then again, we will obtain a vector, right? Because the cross product of two vectors is again a vector. So we have a vector, okay? This is the x component, and this is the y component, and this is the z component. And then we find the magnitude of this vector, right? Because this is what we are required to do in the formula here. And again, it would be very straightforward. We just take the square of each of the component and then sum it up. And then we take the square root, okay, to get the magnitude of the vector, okay? So after some algebra, you should be able to derive the answer, okay, which verifies the result that we should have known already. Okay, so basically this is the workflow. And for the real problem here, things would be a little bit more complicated because we have like three constants, and there is also more trigonometric function like secant and tangent here. But the workflow is basically the same. Okay. Okay. So let's move to the second part of the question. So basically, it's asked to show that the area of a curved surface expressed this way, bounded by two planes, right? The first plane is set equal to 0, and the second plane is set equal to 2a, okay? Is something given by this thing, okay? again, we can see a very similar example by just using the sphere. Okay, so first of all, before we move on to the sphere, we can just take some time to look at this expression. Okay, you can see that this expression is very similar to the very first expression here, which represent the hyperboloid. But it's also a little bit different, right? So you can just try to figure out what you can do to this expression to obtain this one, so that you can simplify the result in A part. Okay, so this is your result, but it can be simplified by using this condition here. Okay, and after you have done so, then you can just go through the algebra that I'm going to show you here. Okay, so basically it's asking for an area, right? And because the result that we have from part A is an area element, so the principle would be to integrate this area element, okay, within an appropriate range to get the area. Okay, so so basically we just integrate the result, okay, integrate the area elements from the range z equals 0 to z equal to 2a. But of course, we won't really do the integration over z because we are not using z in the expression, right? We don't have any z here. Instead, we would integrate over phi and theta, which are the parameters that we're using here. Okay. So how to do it? Well, so let's look at the sphere. Now let's say we were trying to find the area of a sphere, okay, between the plane z equal to 0, which is actually nothing but the xy plane, right? And z equal to a, okay? So this is the xy plane, but it is moved along the z-axis up to a, okay? And we call that the sphere that we are dealing with has radius a. So actually this plane is actually touching the north pole of the sphere. Okay, so the area of a sphere between these two planes is nothing but just the area of the north hemisphere. And we know that the area is actually 2 pi a square. Okay, it's a very simple math. But let's review how to do this, or how to obtain this result by using calculus, by using integration. So again, we obtain the area by integrating the result of part A, which is the element area. And then we just plug in the result into ds here. Okay, and the result would be a squared sine theta and d theta d phi here, right? Okay. But the range that we integrate over d phi and d theta would be 0 to 2 pi and 0 to pi over 2 respectively. Okay, so this should be trivial to you if you're familiar with vector calculus. If you still have some problem understanding this, you may go back to vector calculus to figure this out. Or actually, we can just look back to the definition of z here, right? Because z on the sphere is given by a cosine theta, right? So you can just look at this expression and see what it would become, or what the theta would become when z is 0 and a, right? In that way, you should be able to get the range of theta here, which is 0 and pi over 2. Okay, so what follows would be some algebra, which I think I don't need to spend the time with you here. And the result would be 2 pi a squared, verifying the answer that we know already. Okay, so this is basically the workflow. But I would also like to admit that the real problem here is much more complicated than sphere, okay? Because obviously a tangent and secant are involved, okay? And also from the final answer given by the question, you see that some hyperbolic function is involved, okay? So rather than just integrating so naively like this, maybe you would want to figure out some trick to do the integration, okay? Okay, so this is something that I want to remind you. But basically the workflow is like this, right? Okay, I think it's pretty much what I want to share with you for problem set 1. I hope that this would be helpful to you. I hope that this would provide some hints about how to do the question, do the problem sets. Okay, yeah, so that's all. Thank you very much. I wish you good luck.